All right, unbelievable but true. There are three main methods for finding velocity for linkages. Only one of them requires calculus, and that's the method that students always choose. You've got instantaneous center of zero velocity, velocity polygon, and a complex algebra / loop closure method. So I'm going to solve this problem on the screen here using the complex algebra loop closure method. And the reason students always choose this one is because the calculus is kind of at least straightforward. And if nothing else, it's just like a brute force method that doesn't really require any spatial reasoning. And given the choice between calculus and spatial reasoning / trigonometry, students actually almost always choose the calculus version. So this 6-bar linkage is really split up into two main sections. On the left side, there's a regular 4-bar linkage. And over on the right-hand side, there's a crank slider. And we're given for this problem that the slider over on the side is moving at 20 inches per second. And so we're trying to find then omega 2, which is going to be the angular velocity of the input crank over at O2. Now I'm going to start off this problem over on the crank slider side because that's where we're given information. That's where we have a number to start. And I'm going to write out the loop closure equations. Now, in your textbook, you might find sort of two different versions of this. There's one version that has exponentials, like e to the I theta or e to the j theta. And another version that has sine and cosine. And I strongly, emphatically recommend every single time, just jump straight to the sine cosine version. You've been doing x and y components of vectors all the way since like back in statics. E to the j theta gets a little bit more obscure, a little more abstract, a little bit more like Cal 3. So just stick to sine and cosine. And so on the crank slider side, I'm going to follow this green path, starting at 04, going along link 4, link 5, and then sort of back left and then back up to get back to 04. And as I'm going to write the summation of all these vectors, right, the sum has to add to 0. That is loop closure. If I add these 4 vectors, I end up at where I started. So that means the 4 vectors have to add to 0. And by going straight to sine and cosine, that lets me actually split up the x and y components of these vectors. And all of the x components have to add to 0, and all of the y components have to separately add to 0. What this does is this takes one vector equation and splits it up into 2 vector equations, which lets me solve for 2 unknowns. Those 2 unknowns I'm going to solve for are the 2 angular velocities of these 2 links, 4 and 5. So let's just write down the equations. So in the x direction, starting at 04, we've got 18 cosine theta 4 plus 24 cosine theta 5 minus 27.5, which gets me all the way back just horizontally, and then plus 0, since my final vector is just straight vertical. It's not horizontal at all, and that equals 0, because I ended up back where I started. In the y direction, 18 sine theta 4 is the y component of the first vector, negative 24 sine theta 5, minus 0, because the horizontal section is not vertical, and then plus yd, which, yeah, so, and now I wrote yd here. Of course, that's actually not quite right. So I clearly mislabeled yd on my drawing. This should be the distance from 04 to D, not from C to D. So yd in the equation is correct, but on my drawing is incorrect. Now we could just solve for angles at this point if we wanted to, but we're trying to find velocities. That's the whole purpose of this problem, right? We're trying to solve for velocities. So we need to take a time derivative of both of these equations. So x dot, negative 18 sine theta 4 dot. That theta 4 dot appears because of the chain rule. If you're just taking the derivative of cosine of x, the derivative is negative sine of x. But if x is a function of t itself, then you have to additionally apply the time rule and take the time derivative of x, or in this case, theta. So this is why when taking the derivative of cosine theta 4 dot comes outside because theta 4 changes in time. It itself is a function of time, chain rule, have to take its derivative. So minus 24 sine theta 5, theta dot 5, minus 0 plus 0 equals 0 because the derivative of 27.5 is 0. 27.5 is a constant. The derivative of a constant is 0. So the derivative of the y term, 18 cosine theta 4, theta dot 4, minus 24 cosine theta dot 5, cosine theta 5, theta dot 5, plus 0 plus vd equals 0. So yd, right, that green vector from 0, 4 to d, that distance is changing, right? As the slider moves up and down, yd will change. And the derivative of position is velocity. So that's why in this equation, the time derivative equation, I've changed y, which is position, to v, which is velocity. Now I'm going to take these x dot and y dot expressions and put them into matrix form. So I can quickly, easily solve these just in my calculator. I have a TI-36X Pro, which is a good calculator if you're thinking about taking the FE exam. And in the syssolve section, it can solve a system of linear equations. Right, so this sort of 2x2 is very easy to solve. Just punch in all these numbers and you'll get the answer. So the two variables I'm solving for are theta dot 4 and theta dot 5, so those kind of get pulled out. The first 2x2 matrix is just all of the coefficients. And over on the right-hand side is all of the constants. And so 0 for the x equation. In the y equation, there is a constant, the vd term. So that gets subtracted over to the other side. Of course, before I can push this into my calculator, I need to actually solve for these angles, theta 4 and theta 5. Of course, we have the vd is 20, right? That was the given, the inches per second for point D. So I can just put in that number, negative 20 over there. So in order to solve for theta 4 and theta 5, I'm actually going to start on the 4-bar linkage side, since link 4 is actually on both. It's actually part of the 4-bar linkage and it's part of the crank slider. So if I can solve for the angles over on the 4-bar linkage side, I can apply that to the other side with the crank slider and it'll work out. So start off with a little rough sketch here of this left-hand 4-bar linkage, and I'm going to connect, again, the end of the crank to point 4, and that I'm going to call that L. And I can solve for L just using Pythagorean theorem, because I know the vertical distance is 28 and that horizontal distance is 7, and I get a value of L of 28.86. And now ultimately what I'm really trying to find using all this is theta 4, right? That's the one that's both on the left side and on the right side, theta 4. And if I draw a little horizontal orange line here, you can see that that theta 4 is part of a right triangle. And so if I can find phi1 and phi2, those other two small angles up there, then I'll be able to find theta 4 by just subtracting it from 90, because this is a right triangle. So phi1, I'm now using the triangle that has 18, 24, and L, since phi1 is inside that triangle, and I can do a law of cosines. 24 squared, 24 is the opposite side of the angle, is equal to 18 squared plus 28.86 squared, which is the two adjacent sides, minus 2, the adjacent sides again, cosine theta 1. Some calculator work, 56.01 degrees for phi 1. I think I said theta 1 before I meant phi 1. So phi 2, I actually wrote this out using law of cosines, but I should, since this is actually part of a right triangle, I should have just used like sine or cosine or tangent. But, you know, too late now, law of cosines. So 7 squared, 7 is the opposite side from phi 2. And then 28 and 28.86 are the two adjacent sides. Plug in law of cosines, calculator work, 14.04 degrees now for this angle. Add those together, subtract from 90, and theta 4, 19.95 degrees. And I can go back up to my loop closure equation. Now, the very first x one, so not the derivative equation, but the original x equation, plug in this theta 4 that I found, and solve for theta 5. This theta 5 then ends up being 63.84 degrees. And now plugging in both theta 4 and theta 5, I now have all of the coefficients in the 2x2 matrix. I already had the 0 and the negative 20 on the right-hand side. That lets me plug it into the calculator, right, the system solver. I get theta dot 4, negative 1 radians per second, and theta dot 5 plus 0.286 radians per second. And this seems like we've just finished a whole lot of work. Like, surely we've completed the problem now. And no, this was only actually half of the problem, right? There's two sides to this. We've got the crank slider side and we've got the 4-bar linkage side. We're trying to find for the rotational velocity of the crank. Well, now that we finished half of the problem, looks like your TA Indiana wants a play break, so I guess we gotta go help him out on the hamster wheel. And no, I guess I was wrong. He only wanted to run until I got there, and now I guess it's back to nap time again. Well, nap time for Indy, it's still work time for us. We've still got another second half of this problem still to go. So what we found so far is the rotational velocity of the rocker, basically link 4, which is on both sides. So now what we're gonna do is that whole thing all over again. We're gonna now do loop closure equations, right? This complex algebra method. We're gonna do this on the 4-bar linkage side, but the process is gonna be exactly the same. We're just gonna write the sum of vectors in the x direction, sum of vectors in the y direction, take time derivatives, set up a matrix, solve for any angles that we need, and then plug into the calculator and we'll be done again. And you may be thinking halfway through the problem that, is this really easier? This can't possibly be better than the other ways. This complex algebra method will almost never be the quickest way to solve a problem. Velocity polygon and instantaneous center of zero velocity are almost always faster to solve if you know how. The problem is that they require some spatial reasoning to actually figure out what lengths and what angles you need to find. Takes a little bit of creativity sometimes to solve those problems that way. This problem, even though it takes longer to solve and more calculator work and a little bit of calculus, it's a brute force method. You just do it, just plow ahead and eventually you'll get there. And sometimes it's kind of a relief. It can be frustrating to sit and stare at a problem and not know what to do. At least with a brute force strategy, you're always making progress. Even if it takes a little bit longer, you know you'll get there. Right? So loop closure now on this blue. So I'm gonna start it at ground 2.02, follow the crank, which is link 2, follow the coupler, link 3, the rocker, link 4, straight back down, and then straight back to the left. So in the x direction, 12 cosine theta 2 plus 24 cosine theta 3 plus 18 cosine theta 4 plus 0 minus 19 equals 0. And in the y direction, 12 sine theta 2 plus 24 sine theta 3 plus 18 sine theta 4 minus 28 down plus 0 equals 0. Now we take time derivatives of both. Cosine becomes negative sine, sine becomes cosine, and all of the angles that could change, theta 2, theta 3, and theta 4, these can all change. They all vary with time. Because of the chain rule, we have to add a theta dot term after taking sine. So the derivative of cosine theta 2 is negative sine theta 2 times theta 2 dot, again, chain rule. So now after writing these, at first you'll have a momentary bit of fear that we have 3 variables, theta dot 2, theta dot 3, and theta dot 4. But don't panic, theta dot 4 we already solved on the crank rocker side. So we only actually have 2 unknowns. So putting this into matrix form, we take all the coefficients, gather those on the 2x2 matrix. The 2 unknowns are a vertical term, theta dot 2 and theta dot 3. And then all of the constant terms, which are the sine theta 4, cosine theta 4, and the theta dot 4 terms, all of the known values, those get shifted over to the right-hand side of the equation. Before we were going to be able to plug these into the calculator, we have to actually go back to the drawing and solve for theta 2 and theta 3. Well, theta 2 is given, that's horizontal, so theta 2 is 0, but we need to solve for theta 3. So back up to my 4-bar linkage drawing over here. Theta 3 is going to be the summation of these two, theta 3, 1 and theta 3, 2. So theta 3, 1, it's kind of a tongue twister, is the easier one to find since we already have phi 2 right above it. It's just 90 minus phi 2, so that's going to give us 75.96 degrees. For theta 3, 2, gonna have to do a law of cosines since it's on that left-hand triangle, the big one, and since we know all 3 sides, we can get it with, law of cosines. That works out to be 38.45 degrees, so add these 2 angles together, they combine to be theta 3, 114.41 degrees. So we now plug that in, so now all the coefficients are known, it's just a big calculator problem, put this in your system solver, you get theta dot 2, 1.64 radians per second, theta dot 3, 0.281 radians per second. And I'm going to rewrite angular velocity using omega instead of theta dot. I think theta dot is kind of easier in the equations to keep track between the time derivative, to easier to see which terms kind of line up together. But I'm going to call angular velocity omega 2 1.64 radians per second. And figuring out which direction is this, clockwise or counterclockwise. If D is going down, then C is going down, then B is going up, and A is going up. So omega 2 is going to be in the counterclockwise direction. And I'll just draw the little arrow here, counterclockwise. And so now if you think to yourself, that was kind of long and tedious, but I think I could actually do it, then you're probably like most students taking machinery courses. But if you're interested in a faster solution, then watch one of the videos here about instantaneous center and velocity polygon. Those systems are going to solve problems faster. They require a little bit of spatial reasoning.